Consider two fair six-sided dice. The first is the usual die with the numbers 1 through 6. The second has 2 1s, 2 6s, and a 3 and a 4. Let x be the number shown when the first die is rolled, and y the number shown when the second die is rolled. We find the expected value of the first die is 3.5, and for the second die, we find the expected value of y is the sum of the products of the outcomes with the probabilities, which will be 3.5. However, even though they have the same expected value, they have different distributions. So the probability the first die shows a 2 is 1/6, but the probability the second die shows a 2 is 0 because there are no 2s. So we'd like a measure of the distribution of the random variable. So suppose a random variable x has an expected value. Since x is itself a random variable, we might consider the difference between x and the mean. In other words, what's the expected value of that difference? So we can use our properties of expected value, the expected value of the difference. Again, for reasons that will become apparent soon, we'll want to write that as x plus the negative of the mean. And expected value is linear, so we can split that. And the expected value of x is just the mean, and this becomes negative the mean to give us 0. And intuitively, this makes sense. It says the average difference between the actual value of x and the mean is 0. Now, intuitively, x will sometimes be greater than the mean and sometimes less than the mean. So intuitively, it's not surprising that the expected value is 0, but it's not all that useful. So we might look at the absolute value of the difference, but for reasons this is hard to work with. And it's easier instead to look at the squared difference. And so we define the variance to be the expected value of the squared difference between x and the mean. By definition, the variance is the average value of the squared difference between a random variable and its mean. However, this is hard to compute. So instead, we'll use what's called the computing formula. So let's take that apart. The expected value of the square of the difference, we can expand that. The linearity allows us to break this apart. The mean itself is a constant, so we can remove these constant factors, or just have the expected value of a constant to be the constant itself. And we get, and again, the mean itself is the expected value of the random variable. And so that gives us a nice way to compute the variance. So let's find the variance when we roll a six-sided die. So we've already calculated the expected value, but let's go ahead and put down that computation just to see how we would immediately be able to calculate the expected value of the square. So again, our possible values are 1 through 6, each with probability 1/6. So the expected value of x will be, and for the expected value of x squared, we'll just square those outcomes and get, and so our variance is going to be the difference between the expected value of x squared, 91/6, and the square of the expected value, 21/6. And so we get, now expectation is a linear operator which simplifies the problem of finding the expected value of a function of our random variable. What about variance? First, let's consider the variance of a constant. Using our computing formula, the variance of a constant is the expected value of the square minus the square of the expected value. But remember, the expected value of a constant is just the constant, and so we get, and so let's C be a constant. The variance of the constant is 0. Next, we could consider the variance of a sum, but we'll wait as it's actually kind of complicated. Instead, let's consider the variance of a constant multiple of some function. So again, using our computing formula, the variance is the expected value of the square minus the square of the expected value. We can do a little algebra, and because this is expected value, those constant multipliers can be removed to the front, and we can do a little algebra. And here we have the expected value of a square minus the square of the expected value. That's just our variance again. And so if c is a constant, the variance of a constant times a function is the square of the constant times the variance. So, for example, suppose the price of an airline ticket has a variance of $100. If the tax on a ticket is 8%, what's the variance of the tax? So suppose the price is X, the variance is 100. At 8%, the tax will be 0.08x. And so our variance of Y will be the variance of 0.08x. We can remove the constant factor as its square, and then substitute in our values, we find